All right, the second part. The second part is the more confusing of the two parts. Okay, the first one we kind of already learned. We're just using it in a new way to solve a new type of problem. This one is a little bit different. All right. Fundamental theorem of calculus part 2. If f is continuous, then this has a derivative at every point. That's the derivative. Okay, breaking it down real simple. First of all, whenever you see something that looks like this, it's an accumulation function. Just like when you see this, you should say big F is the antiderivative. When you see this, right away you got to say this function is an accumulation function. What that means is, as I go from point A towards point B, I'm accumulating area under this curve. I'm getting more and more area. All right, you're accumulating area. That's where that comes from. It does not always have to be G. You'll see it as big F sometimes. So you cannot see big F and say it's antiderivative. Big F is the antiderivative if this is written. Okay, so they use big F for this sometimes. They'll use little f for this sometimes. There's lots of different letters they can use. The letters don't mean anything specifically. When you see some function equals the area under this curve, it's an accumulation function. So you got to get that in your heads. All right? Now the derivative part. Basically, if I want to find the derivative of this from some number, any number, this could be any number, as long as it's a number, 0, -5, 18, it doesn't matter. A number to x. The derivative, you just take the x, plug it in, that's the derivative. It's that easy. I'm going to show you the steps behind that in a second. Okay? Very important, this has nothing, t has nothing to do with time here. All right? Common misconception, kids get confused. It's got nothing to do with time. You'll see problems where they'll put a W here. FWDW, FZDZ. As long as it matches, it doesn't matter what letter is there. Okay, they just had to use something different than X, because we have X up here and we're going to plug it in. So don't get hung up on that letter. That letter doesn't mean anything. Okay, function G is an accumulation function because it's accumulating area under the curve. Very important. All right. Here, we'll go over all the algebra right now. Okay, so I start off with just this function from a to x, f of t dt, right? Using the fundamental theorem of calculus part 1, the first part we already knew, all right? I'm going to say big F prime equals little f. What's that mean? Big F's the antiderivative. So using the first part of the fundamental theorem of calculus, we know that this is true. Big F of x minus big F of a. Okay? So this means I found the antiderivative, I plugged in the letter x. And this means I found the antiderivative and I plugged in some number. Remember, a is a number. Okay? So what did I get? Here I got some equation, some function with x's in it. Here I got, when I plug in a number, I get a number. So I got whatever f of x is minus some number. Right? So now, if I want to find the derivative of this, that's the same as finding the derivative of this. What's the derivative of big F? Think about it. Derivative of big F is little f. So the derivative of this would be little f of x. Minus, what's the derivative of any number? 0. So that's how you get the derivative of this is just f of x. Take the x, plug it in. Okay? That's the algebra behind it. You do not have to ever show the algebra, but it helps to understand where it comes from. If I want to find the derivative of the area under a curve from a number, this has to be a number, from a number to x, all you do is plug in x. Now, in a couple minutes, we're going to do where this is not x, this is some equation like x squared. Then you're going to have to do a chain rule kicker. But if it's just x, you just plug it in. So here's our first example. Understand what this equation means before you start. Okay, you see this, you say, oh, okay, G is an accumulation function. So the area under the curve 2t, I'm accumulating area as I move along. So just real quick, let's make a graph of 2t. That's going to be slope 2, so we're going to go like this. Okay? So this is f. Alright? And G is the area under f from, I believe it was 0, from 0 to some x value. So, starting at 0 and going to any x value, as I move along, I am accumulating more and more and more and more area. That's why G is an accumulation function. Okay? The area under the curve is what G is. Back to the last slide. Okay? So G is the area under that curve. Wonderful. So the basic definition, we're using the basic definition here. If I want to know what G of 2 is, that means I'm plugging in 2, substituting in 2, just like you do in a normal function. So the area under this curve from 0 to 2. You could do it by finding the antiderivative, plugging in the points. It's a basic triangle, so you could just do the area under the triangle. Alright? Antiderivative, I would get, the antiderivative of 2t is t squared. Okay, so I got t squared from 0 to 2. That's 2 squared minus 0 squared, which is 4. Basic, just plugging in 2. Alright, next, finding the, looking at the derivative. Alright, if I want to know what g prime is, so I'm just finding the derivative of this. Basic one, from number to x. That means the derivative of this is going to be just plug in x. 2x. Okay, let's go through those steps real quick right now. So if I have 2t from 0 to x, alright, I know that this is the same as, using the first fundamental theorem of calculus, this is the same as antiderivative from 0 to x. So, plug in upper limit, x squared, minus plug in lower limit, 0 squared. So if I want to know what the derivative of this is, I want to know what the derivative of this is. What's the derivative of x squared? 2x. What's the derivative of 0? 0. So there's your answer, 2x. Alright, so here's just another example. I'm not going to go over how to do this step by step. I'm going from a number to x. All I do, derivative, plug in x. Okay? Think about what we have used derivatives for. We can find max and mins using this. We can figure out increasing, decreasing for this. That's our main things for derivatives.